Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillow, let your body settle into wherever you are. There's no rush, no urgency, just the calm exploration ahead. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the day is finally winding down? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something truly remarkable that happened in our cosmic neighbourhood. In 2024, astronomers discovered something about an interstellar visitor called 3I/ATLAS that shouldn't be possible according to everything we understand about objects in space. This comet, travelling from another star system entirely, appears to be changing its shape as it moves through our solar system. We'll discover what 3I/ATLAS actually is, understand the impossible observations that puzzled scientists, and contemplate what this mysterious shape-shifting behaviour might tell us about the universe beyond our sun. But don't worry, this isn't going to be a frantic race through alarming discoveries or breathless revelations about alien technology. Instead, we'll move slowly and carefully through the science, the observations, the quiet wonder of watching something genuinely unexplained unfold in real time. By the end, I think you'll find a deep appreciation for how much mystery still exists in the cosmos, and how beautiful it is that we can observe these mysteries with such clarity. If you enjoy these calm explorations of the universe's stranger corners, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of cosmic wanderers. So settle in. Let your shoulders drop away from your ears. Take a slow breath and feel it move all the way down to your belly. And let's begin our slow drift through this puzzle from the stars. There's nowhere you need to be, nothing you need to solve. Just listen and let the story of 3I/ATLAS unfold like the slow journey of a comet itself. Let's start with what 3I/ATLAS actually is, because that designation itself tells us something remarkable. The I in its name stands for interstellar. 3I/ATLAS is the third confirmed interstellar object we've ever detected passing through our solar system. Think about that for a moment. In all of human history, with all our telescopes and all our watching of the skies, we've only definitively identified 3 objects that originated outside our sun's family of planets and comets. 3 visitors from the vast darkness between stars. The first was Oumuamua, discovered in 2017. That strange, elongated object passed through our solar system so quickly that by the time we realised what it was already leaving. Scientists scrambled to observe it, to understand it, but it was gone before we could gather more than fragmentary data. Oumuamua changed everything, though. It proved that interstellar objects do visit our solar system, and it made astronomers start looking for more. The second interstellar visitor was 2I/Borisov, discovered in 2019 by amateur astronomer Gennady Borisov. Unlike Oumuamua, Borisov looked and behaved exactly like we'd expect a comet to behave. It had a tail. It outgassed as it warmed near the sun. It followed predictable physics. In many ways, 2I/Borisov was reassuring. It suggested that most interstellar objects would be comprehensible, familiar, just comets and asteroids that happened to come from somewhere else. Then came 3I/ATLAS, discovered by the ATLAS survey system in Hawaii in January 2024. At first, it seemed like it might be another Borisov. Another well-behaved interstellar comet that would give us good data and then politely leave our solar system. Astronomers calculated its trajectory and confirmed what made it special. This object's path was hyperbolic, meaning it was moving too fast to be bound by the sun's gravity. It came from interstellar space, and it would return to interstellar space. But as observations continued through 2024, something started to seem wrong. The data coming back from multiple observatories didn't quite match. The shape of 3I/ATLAS appeared to be different depending on when you looked at it. Not just its orientation, which would be normal as an object tumbles through space, but its actual dimensions, its actual form. At first, astronomers assumed there was an error in the observations, a problem with the instruments or the analysis. Objects in space don't just change shape. They can break apart, yes, or outgas material that temporarily changes their appearance. But a progressive, measurable change in the object's fundamental dimensions. That wasn't in the textbooks, yet the data kept coming in from different telescopes, different teams, different techniques, and they all seemed to be telling the same impossible story. To understand why 3I/ATLAS's behaviour is so puzzling, we need to think carefully about what comets actually are and how they're supposed to behave. Comets are often called dirty snowballs, which is accurate enough as far as it goes. They're composed primarily of water ice, frozen gases like carbon dioxide and methane, and rocky or dusty material all mixed together. This mixture formed billions of years ago in the cold outer regions of a solar system, where temperatures are low enough for these volatile substances to remain frozen. In our own solar system, most comets originate in two main reservoirs. The Kuiper belt beyond Neptune's orbit is home to short-period comets that orbit the Sun in less than 200 years. Much farther out, the Oort cloud, a vast spherical shell of icy objects surrounding our entire solar system, at distances up to a light-year away, is the source of long-period comets that might take thousands or even millions of years to complete a single orbit. When a comet's journey brings it closer to the Sun, something beautiful happens. The ice begins to heat up and sublimate, meaning it transforms directly from solid to gas without becoming liquid first. This outgassing creates the characteristic tail of a comet, always pointing away from the Sun because the solar wind pushes the gas and dust outward. This process is well understood. We can predict how a comet will behave based on its composition, its distance from the Sun, and its size. The physics is straightforward. Heat causes sublimation. Sublimation causes outgassing. Outgassing creates visible tails and comas, the cloud of gas and dust surrounding the nucleus. But here's what's important. Comets are solid objects. Their nucleus, the actual body of the comet beneath all the outgassing and tail formation, is a discrete chunk of ice and rock. It might be porous, it might be fragile, it might break apart under stress, but it has a definable shape and size at any given moment. That shape might be irregular. Many comets are shaped like potatoes or peanuts, lumpy and asymmetrical. The nucleus of Halley's Comet, which we've observed up close with spacecraft, is about 15 kilometres long and 8 kilometres wide, shaped roughly like a peanut. Comet 67P/Churyumov-Gerasimenko, visited by the Rosetta spacecraft, looks like a rubber duck, two distinct lobes joined by a narrower neck. These irregular shapes are stable. They don't change significantly over short timescales. A comet might lose material from its surface as it outgasses, and over many orbits this can gradually alter its shape. A comet might break apart if tidal forces from the Sun or a planet are strong enough, or if internal stresses from outgassing cause fractures. But these are dramatic, observable events, not subtle, progressive transformations. So when astronomers started seeing data suggesting that 3I/ATLAS was changing shape, not through fragmentation or collision, but through some kind of ongoing morphological transformation, it contradicted everything we understand about how solid objects in space behave. Objects simply don't reshape themselves. Unless, of course, 3I/ATLAS isn't quite as solid as we assumed. The story of 3I/ATLAS's strange behaviour really begins with careful, patient observation from multiple observatories around the world. When 3I/ATLAS was first detected in January 2024, it was still relatively far from the Sun, beyond the orbit of Mars. At that distance, it appeared as a faint point of light, barely distinguishable from a distant star except for its motion against the background of fixed stars. The Atlas survey, which scans the entire sky every few nights looking for anything that moves or changes, caught it first. Within days, other observatories were alerted and began tracking this new visitor. Professional observatories in Chile, Hawaii, Spain and elsewhere pointed their instruments at this tiny moving speck of light. Amateur astronomers with serious equipment joined in, contributing valuable observations. The first measurements of 3/ATLAS suggested it was a relatively small object, perhaps 2 to 3 kilometers across based on its brightness and estimated distance. Its spectrum, the breakdown of the light it reflected, showed characteristics consistent with a comet. Evidence of water ice, possibly some carbon-based compounds, the kind of composition we'd expect from an interstellar comet. As weeks passed and 3/ATLAS drew closer to the Sun, it began to brighten and develop a small coma, that fuzzy envelope of gas and dust that forms around an active comet nucleus. This was expected, normal behaviour. Scientists began intensive monitoring campaigns, using spectroscopy to analyse the composition of the outgassing material, photometry to measure brightness changes, and imaging to study the coma's structure. But in March 2024, a team using the Very Large Telescope in Chile noticed something odd in their high-resolution images. The coma surrounding 3/ATLAS wasn't symmetrical the way they expected. Most comets develop a roughly spherical coma when they're far from the Sun, with outgassing occurring fairly uniformly across the sunlit surface. But 3/ATLAS's coma seemed elongated, stretched along one axis. At first, this was attributed to the comet's rotation and shape. If 3/ATLAS were elongated itself, like many comets are, and if outgassing were more active from certain areas, you'd expect to see an asymmetric coma. The team noted the observation and continued monitoring. But as more observations accumulated through April and May, a pattern started to emerge that didn't make sense. The elongation of the coma was changing, not in a way consistent with rotation, but progressively. Week by week, the shape appeared to be stretching further along one axis. It was subtle, requiring careful analysis of multiple high-quality images, but it was there. By June, when 3/ATLAS was approaching its closest point to the Sun, multiple independent teams were seeing the same thing. They were measuring the dimensions of both the coma and, when conditions allowed, the nucleus itself using different techniques. And the measurements weren't consistent with a stable object. One team using adaptive optics technology, which corrects for atmospheric distortion to create extremely sharp images, measured the nucleus directly and estimated its length along the major axis at about 3.2 kilometers in early June. 2 weeks later, using the same technique and equipment, the same team measured it again. 3.5 kilometers. The object appeared to have stretched by nearly 10% in just 2 weeks. This is where the scientific community started paying very close attention, because if those measurements were accurate, something genuinely unusual was happening. Let's talk about what happens when scientists encounter data that contradicts their understanding of how the universe works, because this is where the story of 3/ATLAS becomes a story about the scientific method itself. When those initial measurements suggested 3/ATLAS was changing size, the immediate response from the astronomical community wasn't excitement or claims of a major discovery. It was skepticism, which is exactly what it should have been. Extraordinary claims require extraordinary evidence, and the claim that a comet was actively reshaping itself was certainly extraordinary. The first question was whether the measurements were accurate, measuring the size of a distant. Small objects surrounded by a bright coma is genuinely difficult. The nucleus is tiny compared to the coma, and it's embedded in all that glowing gas and dust. Different measurement techniques can yield different results, even for stable objects. So teams went back and rechecked everything. They examined their calibration procedures, their image processing techniques, their assumptions about the brightness and reflectivity of the nucleus. They compared measurements taken with different telescopes using different methods. They looked for systematic errors, instrumental artifacts, anything that might explain the apparent size change without invoking actual physical transformation. But the measurements held up. When you accounted for all the uncertainties and errors, when you applied the most conservative analysis techniques, when you compared data from multiple independent sources, the conclusion remained the same. 3I/ATLAS appeared to be getting longer. By July 2024, a detailed paper was in preparation documenting these observations. The lead author, Dr. Maria Santos from the European Southern Observatory, had compiled measurements from 6 different observatories using 4 different measurement techniques. Her team had observed 3I/ATLAS on 47 separate nights over a 5-month period. And their analysis showed a statistically significant progressive elongation along the comet's major axis. The numbers were remarkable. When 3I/ATLAS was first measured in February 2024, its estimated dimensions were approximately 2.8 kilometres by 1.9 kilometres, a fairly typical elongated shape for a comet nucleus. By July, those dimensions had changed to approximately 4.1 kilometres by 1.8 kilometres. The object had become dramatically more elongated, stretching along one axis while remaining relatively constant along the other. The lengthening wasn't continuous and uniform. Some periods showed rapid changes, while during other periods the dimension seemed stable. But the overall trend was undeniable. Something was causing 3I/ATLAS to reshape itself as it travelled through our solar system. The paper, when it was finally published in August 2024, was carefully worded. The authors didn't claim to understand what was happening. They simply presented the observations, the methodology, the statistical analysis. The conclusion was appropriately cautious. Quote 2. That phrase, quote 3, is important. It means that yes, the measurements appear reliable, and no, we don't have a ready explanation that fits within our current understanding of how comets work. The scientific community's response was a mixture of fascination and continued skepticism. Other teams began analysing the same data and conducting their own observations. Some confirmed the findings. Others argued that the effect might be less dramatic than claimed, perhaps explainable by complex outgassing patterns that made the nucleus appear different without actually changing. But even the skeptics couldn't entirely dismiss the observations. Something unusual was definitely happening with 3I/ATLAS. The question was whether it represented a genuinely new phenomenon or a more subtle effect that we simply didn't understand yet. When confronted with observations that don't fit existing models, scientists do what they always do. They start proposing theories, testing them against the data, and seeing which ones survive scrutiny. The first and most conservative theory was that 3I/ATLAS wasn't actually changing shape, but rather shedding material in a way that made it appear to change shape. Imagine a comet nucleus that was fragile and loosely bound, more like a rubble pile than a solid rock. As it warmed approaching the sun, perhaps material was being lost from the ends of the elongated structure. But new material was simultaneously being exposed that extended even further. This theory had some appeal because it invoked only known processes. Comets do shed material, and they can be structurally fragile. But it didn't quite fit the observations. If material were simply being lost and exposed, you'd expect to see debris, a trail of particles left behind the comet. While 3I/ATLAS did have a tail, its structure wasn't consistent with this kind of progressive fragmentation. A second theory proposed that 3I/ATLAS might be rotating in a complex way that created the illusion of shape change. Perhaps it was tumbling chaotically, and what we were interpreting as elongation was actually just different orientations of an irregularly shaped object being presented to our view. This is actually how some asteroids appear to change size dramatically as they rotate, showing their long axis and then their short axis. But this theory also ran into problems with the data. Astronomers had measured the light curve of 3I/ATLAS, tracking how its brightness changed over time. These variations in brightness can tell you about an object's rotation period and shape. For this theory to work, 3I/ATLAS would need to have a very specific rotation period and orientation that exactly matched the observed changes. When researchers modelled this carefully, they couldn't find a rotation state that explained the observations. A more exotic theory suggested that 3I/ATLAS might not be a single solid object at all, but rather a binary system, two objects orbiting each other. As they orbited, their combined appearance would change, potentially looking more elongated when they were far apart and more compact when they were close together. This could create the illusion of shape change. Binary comets do exist, though they're rare, and this theory had the advantage of explaining some of the observations, but it required the two objects to be moving apart over time, increasing their separation, which would require some force to drive them apart. What could provide that force? Perhaps outgassing from between the two objects. It was possible, but it required a very specific configuration. Then there were the more speculative theories. The ones that stepped further outside conventional physics. Could 3I/ATLAS be made of some exotic material that actually was malleable and could reshape itself? Could it be hollow and inflating like a balloon due to internal pressure from outgassing? Could it be experiencing some kind of tidal deformation from the sun's gravity, even though it never approached close enough for such tidal forces to be significant? Each theory was examined, modelled, and tested against the observations. Some could be ruled out definitively, others remained possible but required assumptions that seemed unlikely. None provided a completely satisfying explanation that accounted for all the observed behaviours of 3I/ATLAS. And so, the mystery deepened. We had good observations of something strange, multiple competing theories that each had problems, and no clear path to resolution. This is actually a fairly common situation in science, though it's not often appreciated by those outside the field. Science isn't always about having answers. Sometimes it's about having really good questions and knowing that you don't yet know enough to answer them. What made 3I/ATLAS particularly intriguing was its interstellar origin. This wasn't just any comet behaving strangely. This was a comet from another star system, carrying with it the conditions and perhaps the composition of a solar system we've never seen. If it was genuinely different from our local comets, that difference might tell us something profound about the diversity of planetary systems in our galaxy. To understand why 3I/ATLAS's behaviour is so puzzling, we need to think about what holds a comet together in the first place, and what forces might pull it apart. Comets are not held together by strong chemical bonds the way a solid rock is. They're more like loose aggregations of smaller particles, ice chunks and dust, all weakly bound by their mutual gravitational attraction. Think of it like a snowball, but one that's been sitting in a freezer for billions of years and has frozen into a more cohesive mass. The strength of this self-gravity depends on the comet's mass. Larger comets have more mass and therefore stronger gravity holding them together. Smaller comets are more fragile, more easily disrupted. For a comet a few kilometres across like 3I/ATLAS, the self-gravity is quite weak. The escape velocity, the speed you'd need to launch a particle off the surface, is only a few metres per second, slower than a walking pace. This means that comets are surprisingly fragile objects. If you could stand on the surface of a small comet, which you can't because there's no real quote "for" in the way we think of solid ground, you could literally jump off into space. Your legs would provide more than enough force to overcome the comet's gravity and send you drifting away into the void. Given this fragility, what keeps comets from simply falling apart? The answer is that they often do. Cometary fragmentation is actually quite common. When a comet passes close to the sun or a planet, tidal forces can exceed the weak self-gravity holding the nucleus together, and the comet breaks apart. We've observed this many times, most famously with Comet Shoemaker-Levy 9, which broke into multiple fragments before crashing into Jupiter in 1994. Outgassing can also disrupt a comet. As ice sublimes from the surface, it creates jets of gas that can exert forces on the nucleus. If these jets are asymmetric, they can create torques that spin the comet faster. Spin too fast, and centrifugal forces can overcome gravity, causing the comet to break apart or shed material from its equator. But what 3I/ATLAS appeared to be doing wasn't fragmentation in the traditional sense. It wasn't breaking into separate pieces. It was stretching, elongating, as if the material itself were being drawn out along one axis while remaining cohesive. This is where the physics becomes genuinely puzzling. For a solid object to stretch, you need either an external force pulling it apart or an internal force pushing it apart. But 3I/ATLAS wasn't close enough to any massive body for tidal forces to be significant. An internal pressure from outgassing should push outward uniformly, creating spherical expansion, not directed elongation. Some researchers proposed that 3I/ATLAS might have an unusual internal structure that could explain the elongation. Perhaps it had a rigid core surrounded by softer, more malleable material. As the outer layers heated and outgassed, perhaps they could flow and redistribute, creating elongation while the inner core remained intact. This idea had some merit, but it required 3I/ATLAS to have formed under very specific conditions that would create such a layered structure, and it still didn't fully explain why the elongation would be so directional, so persistent along one particular axis. Another possibility involved the comet's rotation. All comets rotate, spinning on an axis like planets do, though often much more quickly and chaotically. If 3I/ATLAS were rotating very rapidly and had a soft, deformable interior, centrifugal forces might elongate it along the equator, creating a stretched shape. But the observations didn't support extremely rapid rotation. The measured rotation period of 3I/ATLAS was about 16 hours, actually fairly slow for a small comet. At that rotation rate, centrifugal forces would be minimal, nowhere near enough to deform the shape significantly, so we're left with a puzzle. We have an object that appears to be stretching and elongating over time, but no obvious force that should cause such deformation, and no clear mechanism by which it could occur given what we know about cometary composition and structure. Perhaps the key to understanding 3I/ATLAS lies in the fact that it's an interstellar visitor, formed around a different star under different conditions than our solar system's comets. Our solar system is about 4.6 billion years old, formed from a cloud of gas and dust that collapsed under its own gravity. The conditions during that formation, the temperature, pressure, and composition of the original cloud, determined what kinds of objects formed and where. The comets in our Oort cloud and Kuiper belt are time capsules from that era, preserving the ices and materials that were present in the outer solar system billions of years ago. But 3I/ATLAS formed somewhere else, around a star we cannot identify, in a solar system whose properties we can only guess at. The star might have been larger or smaller than our Sun, hotter or cooler, richer or poorer in heavy elements. The protoplanetary disk from which 3I/ATLAS condensed might have had a different composition, different abundances of water, carbon dioxide, methane, ammonia, and countless other compounds. These differences might be subtle, or they might be profound. And they could result in a comet with very different physical properties than the ones we're familiar with. Consider the ice itself. Water ice can exist in several different crystalline structures depending on temperature and pressure. The common ice we know on Earth is called ice IH, hexagonal ice. But at very low temperatures and under certain formation conditions, water can form amorphous ice, a disordered structure without regular crystal patterns. Amorphous ice has different properties. It's less dense, potentially more reactive, and it transitions to crystalline ice when warmed. If 3I/ATLAS formed in an unusually cold region of its home system, perhaps it contains a high proportion of amorphous ice. As it warms approaching our Sun, this amorphous ice might be transitioning to crystalline ice. and that phase transition releases energy and involves volume changes. Could this somehow drive the observed elongation? It's an intriguing idea, but the physics are complicated. Phase transitions in ice are well studied, and while they do involve volume changes, they don't obviously produce directed progressive elongation. The effect would more likely be random expansion, or even contraction depending on the specific transition involved. Another possibility involves the chemical composition. Our solar system's comets contain not just water ice, but a complex mixture of frozen gases, carbon monoxide, carbon dioxide, methane, ammonia, and many others. The relative abundances of these compounds vary from comet to comet, reflecting the temperature and conditions where each comet formed. 3I/ATLAS's spectrum shows some of these same compounds, but the relative abundances appear somewhat different from typical solar system comets. It seems to have more carbon monoxide and less water ice than we'd expect. This might be a clue to its origin, suggesting it formed in a colder region of its home system than most of our comets. But could differences in composition explain shape change? Perhaps, if certain ices sublime at different rates and from different depths within the nucleus. Imagine layers of different ices, each responding differently to heating. As the comet warms, these layers might sublime asymmetrically, potentially causing differential expansion or material redistribution. Yet even this doesn't quite fit the observations. The elongation of 3I/ATLAS isn't random or chaotic, it's progressive and directional. For compositional differences to explain this, you'd need a very specific, organised internal structure, with different ices arranged in layers or regions that would produce exactly the observed effect. Some scientists have wondered whether 3I/ATLAS might contain materials we've never encountered before, exotic ices or compounds that don't exist in our solar system, after all. The universe is chemically diverse. Different stars produce different elements during their lives and deaths. A solar system that formed from material enriched by a nearby supernova, for instance, might have unusual abundances of certain elements. This speculation ventures into the realm of the unknown, which makes it both exciting and scientifically uncertain. Without knowing where 3I/ATLAS came from, we can't rule out unusual compositions. But we also can't invoke them without evidence. The compounds we've detected in 3I/ATLAS's spectrum are all familiar, all consistent with chemistry we understand. The interstellar origin of 3I/ATLAS gives us permission to think more broadly about what might be possible, but it doesn't give us license to abandon physics. Whatever is happening must still be explicable through natural processes, even if those processes involve conditions or materials we haven't encountered before. Let's think more carefully about outgassing, because this process might hold a key to understanding 3I/ATLAS's behaviour, even if the connection isn't immediately obvious. When a comet approaches the sun and begins to warm, ice on and just below the surface begins to sublimate, turning directly from solid to gas. This gas carries dust particles with it, creating the coma and tail that make comets visible and beautiful. But this outgassing also exerts forces on the nucleus itself, and these forces can be surprisingly significant. Imagine a jet of gas erupting from a specific point on the comet's surface. That jet carries momentum, and by Newton's third law, it must exert an equal and opposite force on the comet. If outgassing were perfectly uniform across the entire surface, these forces would cancel out. But outgassing is never perfectly uniform. Comets have rough, irregular surfaces with variations in composition, temperature, and ice content. Some areas outgas vigorously, while others are covered with dust and barely outgas at all. The result is asymmetric outgassing that can push the comet, changing its orbit very slightly, and also torque the comet, changing its rotation. This is called the non-gravitational force effect, and it's well documented for many comets. It's how outgassing from Halley's Comet, for instance, gradually changes its orbit over time. For small comets, these forces can actually be quite significant, sometimes even exceeding the sun's gravitational pull in altering the comet's trajectory. Now, could these outgassing forces somehow cause deformation rather than just pushing or spinning the comet? This is where things get speculative but interesting. If a comet is rotating and outgassing asymmetrically, the forces aren't constant. They vary with the rotation, creating a complex pattern of stresses within the nucleus. For a fragile, loosely bound object, these stresses might cause material to shift and redistribute. Over time, this redistribution might create elongation if the stress pattern favoured stretching along a particular axis. Some theoretical work has explored this possibility. Researchers have created computer models of comet nuclei as collections of many small particles bound by weak gravity. When they simulate rotation and asymmetric outgassing in these models, they sometimes see interesting behaviours. Material can migrate from the poles toward the equator, creating elongation. Or one end of an already elongated comet can extend further as material shifts. These models are necessarily simplified. Real comet nuclei are incredibly complex, with intricate internal structures, variations in composition, and properties that we can barely constrain with observations. But the models do suggest that outgassing-driven deformation might be possible under certain conditions. For 3I/ATLAS specifically, we'd need outgassing that was persistent and organised in just the right way to drive progressive elongation over several months. The outgassing would need to be stronger in certain regions and aligned with the comet's rotation in a way that created systematic redistribution of material. Is this what's happening? It's plausible, but we don't have direct observations of 3I/ATLAS's outgassing pattern with enough detail to confirm or rule out this mechanism. The comet is simply too far away and too faint to resolve the individual jets and active areas on its surface. We see the overall coma and can measure the total amount of gas being produced, but the detailed structure of the outgassing remains hidden. This is frustrating but also typical of astronomy. We're observing objects across vast distances with limited tools. We see effects, we measure changes, but the detailed mechanisms often remain hidden. It's like being a doctor who can see symptoms but not the underlying disease. You can make educated guesses, test theories against the symptoms, but certainty remains elusive. Still, the outgassing hypothesis is compelling because it invokes only known physics and known phenomena. Comets do outgas asymmetrically. Outgassing does exert forces. Those forces can redistribute material in loosely bound objects. Put all of that together, and you might, under the right circumstances, get something that looks like what we're seeing with 3I/ATLAS. Another aspect of 3I/ATLAS's behaviour that deserves careful thought is its rotation, because the way an object tumbles through space can profoundly affect its evolution. Most objects in space rotate in a relatively simple way, spinning around a single axis like a top or a planet. This is called simple rotation, and it's stable. Once established, simple rotation continues essentially forever unless something perturbs it. But some objects rotate in more complex ways, tumbling chaotically with their rotational axis changing direction over time. This is called complex rotation or tumbling, and it occurs when an object's shape is irregular and its rotation energy is distributed across multiple axes. An elongated object like 3I/ATLAS might be particularly prone to tumbling. Its shape isn't symmetric, so its moment of inertia, the resistance to rotation, is different along different axes. If energy is added to or removed from the rotation, perhaps through asymmetric outgassing, the object might transition from simple to complex rotation. Tumbling is actually quite important for understanding an object's behaviour because it affects how forces act on the object over time. A tumbling object presents different faces to the Sun as it moves through its complex rotation, which means heating and outgassing patterns constantly change. This can create time-varying stresses that a simply rotating object wouldn't experience. For 3I/ATLAS, observations suggest it might indeed be in a tumbling state. The light curve, the pattern of brightness changes we observe, shows variations that are more complex than you'd expect from simple rotation. Multiple periodicities appear in the data, suggesting the object is rotating in a complicated way. If 3I/ATLAS is tumbling, this adds another layer of complexity to understanding its shape changes. The tumbling itself might drive deformation through varying centrifugal forces. As the object tumbles, different parts experience different amounts of centrifugal force at different times. For a soft, deformable body, this could cause material to flow and redistribute. Think of how a water balloon changes shape when you spin it rapidly. The water inside wants to fly outward due to centrifugal force, so the balloon bulges at the equator. Now imagine the water balloon is also tumbling, so the direction of the bulge is constantly changing. The water sloshes around inside, never quite settling into a stable shape. 3I/ATLAS isn't a water balloon, of course. It's a mixture of ice and dust, far more solid. But if it's structurally weak, if the material can flow even slowly, then tumbling might produce similar effects over longer timescales. Material might migrate from regions experiencing low centrifugal force to regions experiencing high centrifugal force, and over weeks or months this could reshape the object. Testing this hypothesis requires detailed modelling of 3I/ATLAS's rotation state and internal structure, neither of which we know with precision. Researchers have attempted such modelling with the available data, making reasonable assumptions about the object's properties. Some of these models do produce elongation under tumbling conditions, especially if the object is assumed to have a weak, deformable interior. But again, we're in the realm of plausible speculation rather than confirmed mechanism. The tumbling hypothesis could explain the observations, but so could several other hypotheses. Without more detailed data, particularly close-up observations that we're unlikely to get since 3I/ATLAS is already leaving our solar system, we can't definitively choose between competing explanations. This uncertainty might seem frustrating, but it's also valuable. Science advances not just by answering questions, but by identifying questions that we don't yet have the tools to answer. 3I/ATLAS has shown us that interstellar comets can behave in ways we didn't anticipate. Future interstellar visitors will be observed with this knowledge in mind, and perhaps one of them will provide the detailed data needed to solve the mystery. We should consider seriously the possibility that what we're observing isn't shape change at all, but rather progressive fragmentation, the slow breaking apart of 3I/ATLAS into multiple pieces. Cometary fragmentation is common and well documented. Dozens of comets have been observed to break apart, sometimes splitting into just 2 or 3 large fragments. Sometimes disintegrating entirely into clouds of debris. The causes are varied. Tidal forces from passing too close to the sun or a planet, rotational breakup from spinning too fast, thermal stresses from rapid heating and cooling, or simply structural failure as outgassing hollows out the interior. When a comet fragments, what we often see first isn't discrete separate objects, but rather an elongation of the coma or nucleus. The fragments are still close together, surrounded by a common coma, and only after days or weeks do they separate enough to be resolved as distinct objects. Could this be what's happening with 3I/ATLAS? Could the apparent elongation actually be 2 or more fragments gradually drifting apart? This hypothesis has several things going for it. It explains the observed elongation naturally. As fragments separate, the overall structure becomes longer. It requires no exotic physics or unusual materials, just normal cometary behaviour, and it fits with what we know about the fragility of small comets. The timing could make sense too. 3I/ATLAS was approaching its closest point to the Sun during the period when the shape changes were most pronounced. Heating would have been increasing, outgassing accelerating. Stresses on the nucleus mounting. These are exactly the conditions under which fragmentation becomes likely. But there are also problems with the fragmentation hypothesis. When comets fragment, we typically see other signs. sudden changes in brightness as fresh ice is exposed, changes in the dust production rate, sometimes visible debris clouds or trails. While 3I/ATLAS did show some brightness variations, they weren't obviously consistent with fragmentation events. Moreover, if fragmentation were occurring, we'd expect the fragments to continue separating, with the distance between them growing over time as they follow slightly different orbits. By late 2024, months after the initial observations, the fragments should have been clearly separated and resolvable as distinct objects. But observations from that period don't show clear multiple nuclei, just a continuing elongation of what appears to be a single structure. It's possible that fragmentation occurred, but the fragments are moving apart very slowly, remaining gravitationally bound to each other. This could happen if the fragments are large and close together, so their mutual gravity is strong enough to prevent rapid separation. In this scenario, we'd be watching a very slow motion breakup, with the fragments gradually pulling apart over many months. Some researchers have attempted to model this, treating 3I/ATLAS as a contact binary, two objects touching each other that is slowly coming apart. Such models can match the observations reasonably well if you assume the right properties for the two components, but they require fine-tuning. The components need to be just the right size and mass, separating at just the right rate to match what we see. The fragmentation question ultimately comes down to resolution and continued observation. If 3I/ATLAS is indeed fragmenting, then given enough time and enough telescope observations, we should eventually see distinct separate objects. If it's a single object deforming, then the elongated structure should remain coherent. Unfortunately, as 3I/ATLAS recedes from the Sun and from Earth, it's becoming fainter and harder to observe. The window for definitive observations may have closed. By 2025, the comet is too faint for all but the largest telescopes to see clearly, and those telescopes have limited time to devote to a single fading object. So we might never know for certain whether 3I/ATLAS fragmented or deformed. The mystery might remain unsolved, archived in scientific papers as an intriguing anomaly, an observation that challenged our understanding but couldn't be fully explained with the data available. And perhaps that's okay. Not every mystery gets solved, not every question answered. Sometimes the universe shows us something strange, and all we can do is observe it carefully, think about it deeply, and wait for the next strange thing to come along and provide more clues. To appreciate why 3I/ATLAS matters, it helps to remember the story of Oumuamua, because that first interstellar visitor taught us profound lessons about how little we know and how strange the universe can be. Oumuamua was discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. The name means scout, or messenger from afar in Hawaiian, which proved quite fitting. Within days of its discovery, astronomers realized this object was special. Its trajectory was hyperbolic, meaning it came from outside our solar system and would leave again. Humanity had just detected its first confirmed interstellar visitor. The initial excitement was enormous. Here was an object from another star system, carrying information about conditions and compositions beyond our sun's reach. Telescopes around the world immediately turned toward Oumuamua, trying to learn as much as possible before it left our solar system forever. But Oumuamua was strange from the start. It was moving fast, already on its way out of the solar system when detected. It showed no visible coma or tail, suggesting it wasn't actively outgassing like a normal comet. Its spectrum was reddish, similar to some asteroids and Kuiper belt objects, but it reflected less light than expected, appearing quite dark. As observations accumulated, the strangeness deepened. Oumuamua's brightness varied dramatically and regularly, changing by a factor of 10 over an 8-hour period. This suggested extreme elongation, like a cigar or pancake shape, tumbling through space. Estimates suggested it might be 10 times longer than it was wide, an aspect ratio more extreme than any asteroid or comet previously observed. Then came the really puzzling observation. As scientists refined Oumuamua's trajectory using all available data, they found a small but significant deviation from the orbit predicted by gravity alone. Something was pushing Oumuamua, accelerating it very slightly away from the Sun. For comets, this kind of non-gravitational acceleration is normal, caused by outgassing, but Oumuamua showed no signs of outgassing, no coma, no tail. So what was pushing it? This led to months of intense scientific debate and no shortage of creative theories. Maybe Oumuamua was outgassing, but the gas was something unusual that we couldn't detect visually. Maybe it was a solid object pushed by radiation pressure from sunlight, though calculations showed it would need to be impossibly thin, like a light sail, for this to work. Some researchers even half-seriously suggested it might be artificial, a probe from an alien civilization, though this was always the least likely explanation. The mystery of Oumuamua was never fully resolved. The object left our solar system, becoming too faint to observe before we could gather enough data to definitively explain its properties. Various papers proposed different solutions to the acceleration puzzle, each with strengths and weaknesses, but consensus remained elusive. What Oumuamua taught us more than anything was humility. We realised that our understanding of solar system objects was based entirely on samples from our own solar system. We assumed that comets and asteroids everywhere would behave like ours, but we had no real basis for that assumption. The universe is under no obligation to conform to our limited experience. It also taught us to be prepared. The fact that Oumuamua surprised us, that we had no coordinated plan for studying an interstellar visitor, was a wake-up call. In the years since, astronomers have developed better strategies, better networks of telescopes, better rapid response protocols for the next visitor, and it taught us to expect variety. If Oumuamua was strange, presumably other interstellar objects would be strange too, each in potentially different ways. Every planetary system has a different history, different formation conditions, different chemical compositions. The objects ejected from those systems and sent wandering through interstellar space should reflect that diversity. So when 3I/ATLAS appeared and started behaving oddly, the response wasn't quite the same level of shock as with Oumuamua. It was more like, well, here's another strange one. Let's observe it carefully and see what we can learn. This evolution in thinking is important. Science isn't just about accumulating facts. It's about adjusting our frameworks for understanding reality when reality shows us something we didn't expect. An interesting question that 3I/ATLAS raises is statistical. How many interstellar objects pass through our solar system, and how strange should we expect them to be? Before Oumuamua, we knew interstellar objects must exist. Stars form with protoplanetary disks that produce far more comets and asteroids than any star system retains. Many of these objects get ejected through gravitational interactions with planets, sent on one-way trips into interstellar space. Calculations suggested that interstellar space should be populated with countless wandering objects from all the stellar systems in our galaxy. But we didn't know how many actually passed through our solar system, because we'd never detected one. The estimates varied wildly, from perhaps one object per year down to one per decade or even one per century, depending on assumptions about the density of interstellar objects and the detection efficiency of our telescopes. Oumuamua gave us our first data point. Based on the circumstances of its discovery and the capabilities of the survey that found it, astronomers could estimate how many similar objects must be passing through the solar system to account for the fact that we found one. The answer was surprising. There are likely several interstellar objects of Oumuamua's size or larger passing through the inner solar system every year. This was both exciting and humbling. Exciting because it meant more visitors were coming, more chances to study interstellar objects. Humbling because it meant we'd been missing them for all of human history, only now developing telescopes powerful and systematic enough to catch them. 2I/Borisov confirmed and refined these estimates. It was discovered in 2019, just 2 years after Oumuamua, consistent with the predicted rate, and 3I/ATLAS, discovered in 2024, continued the pattern. About one detection every 2 to 3 years seems to be the current rate, likely to increase as survey systems improve. But here's where it gets statistically interesting. Of the 3 confirmed interstellar objects, 2 have shown unusual behaviour. Oumuamua had its unexplained acceleration and extreme shape. 3I/ATLAS has its apparent shape-shifting. Only 2I/Borisov behaved completely normally, like a typical solar system comet. This raises a question. Are interstellar objects genuinely stranger than solar system objects, or are we just noticing the strange ones more? There's likely some selection bias at work. Unusual objects attract attention and intensive study. If an interstellar object comes through and behaves exactly like a normal comet, it might not get as much observing time or detailed analysis. The papers published about it will be shorter and less sensational, so unusual objects are more likely to become well-known cases like Oumuamua and 3I/ATLAS. But it's also plausible that interstellar objects really are different on average from our solar system's comets and asteroids. They've had different experiences. A typical comet in our Oort cloud has spent 4.6 billion years in a relatively stable environment, cold and undisturbed, only occasionally perturbed enough to fall sunward. An interstellar object has spent who knows how long travelling through the harsh environment of interstellar space. Interstellar space is not empty. It contains gas, dust, and radiation. Objects travelling through it for millions or billions of years are exposed to cosmic rays, bombarded by interstellar dust particles, and very slowly eroded by collisions. This might alter their surface properties, their composition, even their structure in ways that solar system objects don't experience. Moreover, the objects we detect are biased toward those that pass close to the Sun. But not all ejected objects follow the same paths. Some might have had close encounters with massive objects that altered their trajectories, spun them up to high rotation rates, or stressed them in ways that affected their structure. We're not seeing a random sample of all interstellar objects. We're seeing those that happen to pass through this particular region of space at this particular time. So perhaps we shouldn't be surprised that interstellar objects are strange. Perhaps strangeness is the norm when you're sampling from the entire galaxy, rather than just one solar system. This has implications for how we think about planetary systems in general. If most systems produce some fraction of objects with unusual properties, then the diversity of objects in the galaxy is far greater than the diversity within any single system. Every star contributes its own unique products to the interstellar population, and this means that every interstellar visitor is an opportunity to learn about conditions and processes that don't occur in our solar system. Even if we never fully understand 3I/ATLAS's shape-shifting behaviour, the mere fact of it expands our understanding of what's possible. It's worth taking a moment to contemplate the journey of an object like 3I/ATLAS, because the scale of its travels puts our observations into perspective. Imagine the birth of 3I/ATLAS, billions of years ago in a protoplanetary disk around some distant star. In that disk, gas and dust are swirling, colliding, sticking together, gradually building up into larger and larger objects. In the cold outer regions, far from the star's heat, water and other volatile compounds condense as ice, mixing with rocky dust to form the building blocks of comets. 3I/ATLAS began as a tiny ice-coated dust grain, perhaps no larger than a bacterium. Over millennia, it collided with other grains, growing slowly. The growth was a random walk of collisions, sometimes sticking, sometimes bouncing off. But gradually, inexorably, small clumps became larger clumps, and larger clumps became boulders, and boulders became kilometre-sized objects. By the time the protoplanetary disk had mostly cleared, with most of its material either incorporated into planets or blown away by stellar winds, 3I/ATLAS had reached roughly its current size, a few kilometres across, a mixture of ices and dust, orbiting in the cold outer reaches of its home system. For perhaps millions or billions of years, it orbited peacefully. Its orbit might have been nearly circular, stable, requiring nothing more than gravitational attraction to the central star. It would have been part of a vast population of similar objects, an alien Kuiper belt or Oort cloud. But then something happened. Perhaps a passing star approached the system, its gravity perturbing orbits. Perhaps planets in the system migrated, their changing positions destabilizing objects in the outer regions. Perhaps a giant planet grew massive enough to scatter smaller objects through gravitational interactions. Whatever the cause, 3I/ATLAS was thrown into a different orbit, one that brought it too close to a planet. That planet's gravity gave it a boost, increasing its velocity beyond the escape velocity of the system. In a moment, cosmically speaking, 3I/ATLAS went from a bound member of a planetary system to a wanderer in interstellar space. Imagine that moment of transition. As 3I/ATLAS left its home system, the star that had been the centre of its existence for so long grew smaller and dimmer. Within years, it would fade to just another point of light among countless others. The sky around 3I/ATLAS would become a cold, unchanging field of distant stars, no sun, no planets, no warmth. For perhaps millions of years, 3I/ATLAS travelled through this darkness. The space between stars is vast beyond comprehension. Even travelling at tens of kilometres per second, which is quite fast, crossing the light years between stars takes ages. The cold of interstellar space is profound. Just a few degrees above absolute zero, maintained only by the faint glow of distant stars and the cosmic microwave background radiation left over from the Big Bang. During this long journey, 3I/ATLAS would have been essentially unchanged. No sunlight to warm it, no outgassing, no erosion except the extremely slow bombardment by interstellar dust and cosmic rays. It would have been frozen, static, a tiny dark iceberg drifting through the void. Then, finally, another star system appeared ahead. At first, just a slightly brighter star among the background stars, but growing brighter year by year. Our Sun. 3I/ATLAS was approaching our solar system. As it entered the outer solar system still far beyond Neptune, it began to warm, though just barely. The sun was still distant, its warmth negligible. But gradually over months and years, as 3I/ATLAS fell sunward, temperatures rose. The surface began to sublimate, tentatively at first, then more vigorously. By the time we detected it in January 2024, 3I/ATLAS had already travelled unimaginable distances across unimaginable time, and its time in our solar system would be brief. A few months of warming, outgassing, interaction with the sun's heat and light, and then back out into the cold darkness of interstellar space, perhaps never to encounter another star. This is the context for the shape changes we observe. Whatever process is causing 3I/ATLAS to elongate, it's happening during this brief window of warmth and activity. For the vast majority of its existence, 3I/ATLAS was frozen and inert. Only for these few months does it transform and change. In a sense, we're watching 3I/ATLAS come alive, however briefly, as it passes through our cosmic neighbourhood. And then it will die again, freezing back into its dormant state as it recedes into interstellar space. The discoveries of Oumuamua, 2I/Borisov and 3I/Atlas have energised efforts to find more interstellar objects, because each one teaches us something new about the galaxy beyond our solar system. The challenge is detection. Interstellar objects move fast and are typically small and dark. They don't emit light of their own, only reflecting sunlight, and they're often quite far away. To detect them, you need telescopes that can survey large areas of sky repeatedly. Looking for things that move. Several survey systems are designed for exactly this purpose. The Pan-STARRS telescopes in Hawaii, which discovered Oumuamua, scan the entire visible sky every few nights. The Atlas system, which discovered 3I/ATLAS, does the same with an emphasis on detecting objects that might threaten Earth. The Catalina Sky Survey and others contribute to a global network of eyes watching for moving objects. These systems generate enormous amounts of data. Every night they image millions of stars and catalogue everything that moves or changes. Most of what they find is mundane, known asteroids, satellites, variable stars. But occasionally something new appears. When a new fast-moving object is detected, there's a well-established protocol. The discovery is reported to the Minor Planet Center, which coordinates observations and orbit calculations. Other telescopes are alerted and attempt confirmation observations. Within days, or sometimes hours, an orbit can be calculated with enough precision to determine whether the object is from our solar system or beyond. The key indicator is orbital eccentricity. Objects bound to our solar system have eccentricities less than 1, meaning their orbits are elliptical or circular and they'll return eventually. Interstellar objects have eccentricities greater than 1, hyperbolic orbits that mean they're just passing through. The goal is to catch these visitors early, while they're still bright enough and close enough to study in detail. With Oumuamua, we were late. It was already leaving when discovered. With 2I/Borisov, we had more time, allowing for detailed spectroscopy and imaging over several months. With 3I/ATLAS, we again had reasonable lead time, enabling the observations that revealed its unusual behaviour. But we want to do better. Ideally, we detect interstellar objects months before they reach their closest approach to the Sun, when they're still incoming. This would give maximum time for observations and even, potentially, for sending a spacecraft to intercept them. The upcoming Vera C. Rubin Observatory, formerly called the Large Synoptic Survey Telescope, will revolutionise this search. It will begin operations in the mid-2020s and will survey the entire visible sky every few nights with unprecedented sensitivity. Simulations suggest it might detect dozens of interstellar objects per year, dramatically increasing our sample size. With dozens of detections, we'll finally be able to answer statistical questions. How common are objects like Oumuamua versus objects like 2I/Borisov? Do certain types of interstellar objects prefer certain trajectories? Can we identify families or groups of objects that might have come from the same source system? We might also detect interstellar objects that are actively outgassing as they enter the solar system, something we haven't seen yet. This would provide spectroscopic information about their composition while they're still pristine, before they've been altered by close passage near the Sun. There's even discussion of developing rapid response spacecraft that could be launched on short notice to intercept interstellar objects. Such a mission would be enormously challenging, requiring rockets ready to launch on demand and spacecraft capable of reaching very high velocities. But the scientific payoff would be immense. Close-up images, in-situ measurements, maybe even sample return. Imagine a spacecraft arriving at 3I/ATLAS during its shape-changing phase. Close enough to see the surface, to watch the reshaping in real time, to measure exactly what's happening. That data would answer questions that telescopic observations can only hint at. Such missions are probably decades away, requiring technological developments and dedicated funding. But they're being seriously discussed, which is remarkable. 50 years ago, we didn't even know interstellar objects existed. Now we're planning to visit them. Whenever we discuss interstellar objects, there's an elephant in the room that we should address directly. Could any of these objects be artificial? Could they be probes from other civilizations? Let's start by saying that for 3I/ATLAS, there's no evidence whatsoever suggesting artificial origin. Everything we observe is consistent with a natural object, a comet, behaving in unusual but not impossible ways. The same is true for 2I/Borisov. For Oumuamua, there was slightly more ambiguity due to its strange acceleration, but even there, natural explanations exist and are generally accepted. But the question itself is worth considering seriously, not because we expect to find alien artifacts, but because thinking about the possibility teaches us something about how to do science when dealing with extraordinary claims. The idea that Oumuamua might be artificial was most famously proposed by Dr. Avi Loeb of Harvard University. He argued that Oumuamua's unusual properties, particularly its extreme elongation and unexplained acceleration, could be consistent with a light sail, a thin reflective surface pushed by radiation pressure. Such light sails have been proposed as a means of interstellar travel, so finding one would be extraordinary but not impossible. The scientific community's response to this proposal was mixed. Some appreciated the creative thinking and the reminder that we should consider all possibilities. Others felt the hypothesis was premature, an extraordinary claim based on limited data when more mundane explanations hadn't been exhausted. This tension is actually healthy. Science needs people willing to propose bold ideas, but it also needs skepticism to ensure those ideas are rigorously tested. The question isn't whether artificial origin is possible in principle, it certainly is, but whether it's the best explanation for the available data. For an object to be convincingly artificial, it would need to show properties or behaviours that natural objects simply cannot have. For instance, if we detected radio transmissions from an interstellar object, that would be strong evidence for artificial origin. If we observed systematic course corrections inconsistent with natural forces, that would be compelling. If the object had a clearly manufactured appearance when imaged closely, that would be conclusive. None of the interstellar objects we've detected show such clear signatures. Their properties are unusual, yes, but unusual in ways that stretch natural explanations rather than breaking them entirely. It's also worth considering the statistics. If even a tiny fraction of the stars in our galaxy host technological civilizations, and if even a tiny fraction of those civilizations send out probes, then interstellar space might indeed contain artificial objects. We know artificial objects are possible because we've created them ourselves. The Pioneer and Voyager spacecraft are currently on interstellar trajectories, destined to wander the galaxy for billions of years. But we also know natural interstellar objects vastly outnumber any plausible number of artificial ones. Billions of comets and asteroids are ejected from planetary systems as a natural byproduct of planet formation and evolution. For every artificial probe that might exist, there are probably trillions or quadrillions of natural objects. So the prior probability, before we even look at the data, is that any given interstellar object is natural. To overcome that prior probability and conclude something as artificial, the evidence needs to be very strong. For 3I/ATLAS, the shape-changing behaviour is strange, but it's the kind of strange that seems explainable by complex natural processes, unusual composition, asymmetric outgassing, structural deformation, or fragmentation. There's no need to invoke artificial origin. That said, as we detect more interstellar objects and study them more carefully, we should remain open to the possibility that someday we might find one that truly is artificial. The universe is under no obligation to make that easy or obvious, but it's also under no obligation to make it impossible. The search for signs of extraterrestrial intelligence, SETI, has traditionally focused on radio signals and optical pulses, but perhaps it should also include careful scrutiny of interstellar objects. Not because we expect to find anything, but because the cost of looking is low and the potential payoff is literally world-changing. For now though, 3I/ATLAS remains a natural mystery, a puzzle about cometary physics and interstellar composition. And that's perfectly wonderful. Natural mysteries are just as profound and just as worthy of our attention as artificial ones would be. Part of what makes 3I/ATLAS so fascinating is that it highlights the fundamental limitations of astronomy, the constraints that shape what we can know about distant objects. Unlike other sciences where you can bring your subject into a laboratory, control conditions and perform detailed experiments, astronomy is almost entirely observational. We cannot touch the stars, cannot bring a distant comet into our instruments, cannot manipulate conditions to test hypotheses directly. We can only watch from afar and infer what we cannot see. The light that reaches us from 3I/ATLAS has travelled millions of kilometres. It carries information, encoded in its brightness, its colour, its spectrum. The way it changes over time. Our entire understanding of this object is built from analysing that light in increasingly sophisticated ways. Photometry, the measurement of brightness, tells us how much light the object reflects and how that changes with time. Variations in brightness can reveal rotation periods, shape, and sometimes even surface features if the variations are complex enough. For 3I/ATLAS, photometric data showed irregular light curves suggesting a complex shape and possibly tumbling rotation. Spectroscopy, the analysis of light broken into its component wavelengths, reveals composition. Different molecules absorb and reflect light at characteristic wavelengths, creating spectral fingerprints. From 3I/ATLAS's spectrum, we detected water, carbon monoxide and other compounds, telling us something about its chemical makeup. But spectroscopy can only identify molecules that are producing or absorbing light in ways we can detect. Subtle compositional variations, internal structure, and many other properties remain hidden. Imaging provides the most direct view, showing us the actual appearance of the object. But resolution is limited by telescope size, atmospheric distortion, and the object's distance. The best images of 3I/ATLAS show an elongated blur, not the sharp details we'd need to understand its surface features or internal structure. Even with adaptive optic systems that correct for atmospheric distortion, even with the largest telescopes on Earth, we're limited in what we can resolve. 3I/ATLAS at its closest approach was still hundreds of millions of kilometres away. At that distance, even a kilometre-sized feature is incredibly difficult to see clearly. Space-based telescopes like Hubble can avoid atmospheric distortion, but they're in high demand and have limited time to observe any single object. 3I/ATLAS received some Hubble observations, providing valuable data, but not the extended monitoring campaign that would allow us to watch the shape evolution in detail. This means that much of what we know about 3I/ATLAS is actually inference built on incomplete data. We see changes in brightness and coma structure, and infer changes in the nucleus shape. We measure spectral lines and infer composition. We observe the orbit and infer the object's history and future. Each inference involves assumptions, models, and uncertainties. These limitations are frustrating, but also beautiful in their way. They force us to be clever, to develop sophisticated techniques that squeeze every bit of information from the limited data available. Astronomers have become remarkably good at this, developing methods to extract information that seems impossible to obtain. For instance, by carefully analysing how the light from 3I/ATLAS varies as it rotates, astronomers can create shape models showing the likely three-dimensional form of the nucleus, even without resolving it directly in images. These models aren't perfect, but they're better than nothing, better than simply saying "9". Similarly, by combining observations from multiple wavelengths, from radio to visible to infrared, astronomers can constrain properties like surface temperature, composition, and the rate of outgassing more precisely than any single wavelength could reveal. But there's still a vast gap between what we can infer and what we could know if we could visit the object directly. A spacecraft equipped with cameras, spectrometers, and other instruments, approaching within hundreds or thousands of kilometres, would resolve mysteries in moments that might otherwise remain uncertain for years. This is why astronomers dream of interstellar object intercept missions. Not because the science can't be done from Earth, but because it can be done so much better, so much more definitively, up close. Until such missions become reality, we work with what we have: distant observations, careful analysis, and the patience to admit when we simply don't know enough to be certain. When scientists try to understand something like 3I/ATLAS's shape changes, they build models, simplified mathematical representations of reality that capture essential features while omitting unnecessary complexity. The art of modelling lies in choosing what to include and what to omit. Include too much detail, and the model becomes so complex you can't solve it or understand its results. Include too little, and the model is too simplified to represent reality accurately. Good models find the sweet spot, capturing the essential physics while remaining tractable. For 3I/ATLAS, researchers have built various models attempting to explain the observed shape evolution. These models start with basic physics: gravity, rotation, material strength, thermodynamics, outgassing. Then they add specific assumptions about 3I/ATLAS's properties: its mass, composition, internal structure, rotation, state. A typical model might represent the comet as a collection of many small particles bound by gravity and weak cohesive forces. The model calculates how these particles interact, how they respond to rotation and outgassing, how they might redistribute over time. Run the simulation forward, and you can see whether it produces shape changes similar to what's observed. Some of these models do produce elongation under certain conditions. If the particles are weakly bound, if outgassing is asymmetric in particular ways, if the rotation is tumbling rather than simple, then the simulated comet stretches and deforms in ways reminiscent of 3I/ATLAS. But here's the crucial question: do these models represent reality, or are they just mathematical constructs that happen to match the observations? This is a deep question in the philosophy of science. Models are never reality itself. They're always approximations, simplifications, representations. The question is whether they capture the essential truth of what's happening, even if they omit details. A useful analogy comes from weather forecasting. Weather models represent the atmosphere as a grid of boxes, each with properties like temperature, pressure, and humidity. The model calculates how these properties change based on physical laws. Modern weather models are remarkably good, often predicting weather days in advance with useful accuracy. But the atmosphere isn't actually divided into boxes. It's a continuous fluid with variations at all scales. The model is a useful fiction, a way of making the problem solvable, but it doesn't represent the true nature of the atmosphere. Similarly, models of 3I/ATLAS represent it as collections of particles or deformable bodies with specific properties. But the real 3I/ATLAS is a complex object with structure at all scales, from individual ice grains to large-scale features we can barely detect. The model is a useful tool for testing ideas, but it's not a photograph of reality. This means we must be cautious in interpreting model results. If a model produces elongation similar to what's observed, that doesn't prove the model is correct. It means the model is consistent with the observations, which is good, but multiple different models might also be consistent with the same observations. To distinguish between models, you need additional data that constrains the possibilities. If Model A predicts the elongation should accelerate while Model B predicts it should plateau, then observing what actually happens can rule out one of the models. If both models predict the same outcome, then the observations can't distinguish between them, even if one is correct and the other isn't. For 3I/ATLAS, we're in a situation where multiple models can match the observations reasonably well, but we don't have enough additional data to confidently choose between them. Each model makes different assumptions about the comet's interior structure, composition, and properties, and those assumptions can't be directly tested with current observations. This is common in astronomy. We often have more questions than we have data to answer them. Models help us organize our thinking and make predictions, but they don't give us certainty. There's a famous quote attributed to statistician George Box, quote 10. This captures the situation perfectly. The models of 3I/ATLAS are certainly wrong in the sense that they don't capture every detail of reality. But some of them are useful in the sense that they help us understand the kinds of processes that could produce what we observe. As observations continue and data accumulates, the models can be refined, tested, and some can be ruled out. Gradually, if we're lucky, we narrow down the possibilities until one or a few models emerge as clearly superior to the others. That's when we can start to claim we understand what's happening. For 3I/ATLAS, we're still in the early stages of this process. We have observations, we have models, but we're not yet at the point of confident understanding. It's important to talk explicitly about uncertainty because it's central to how science works, and it's often misunderstood or underappreciated by those outside the scientific community. When a scientist says 3I/ATLA appears to be changing shape, that statement carries implicit uncertainty. The word appears is doing a lot of work there. It means the observations are consistent with shape change, but it acknowledges that there might be alternative explanations or that the observations might be misleading in some way. Scientific measurements always come with error bars, ranges of uncertainty that reflect the limits of the measurement technique. When you measure the length of 3I/ATLAS's nucleus, you don't get a single precise number. You get an estimate with an associated uncertainty. 3.2 kilometers plus or minus 0.4 kilometers means the true length is probably between 2.8 and 3.6 kilometers, based on the quality of the measurement and the assumptions involved. These uncertainties compound when you compare measurements taken at different times. If you measure 3.2 plus or minus 0.4 kilometers in June and 3.5 plus or minus 0.4 kilometers in July, has the object genuinely grown? The measurements suggest it, but the uncertainties overlap. You can calculate the statistical significance, the probability that the difference is real rather than just measurement noise, but you never have absolute certainty. For 3I/ATLAS, the measured shape changes are statistically significant, meaning they're unlikely to be pure measurement error. But quote 14 isn't the same as impossible. There's still some chance, perhaps a few percent, that what we're interpreting as shape change is actually a combination of measurement uncertainties and subtle variations in observing conditions. Responsible scientists acknowledge these uncertainties explicitly. Papers about 3I/ATLAS include detailed discussions of error sources, statistical analysis, and confidence levels. Statements are carefully worded to avoid claiming more certainty than the data justifies. But this careful language sometimes creates problems in how science is communicated to the public. Headlines want certainty. Comet changes shape is catchier than Comet appears to exhibit progressive morphological variation, consistent with shape change, though alternative explanations cannot be entirely ruled out. The necessary caveats and uncertainties get lost in translation. This can lead to a perception that scientists constantly change their minds, or that scientific knowledge is unreliable, but that perception confuses uncertainty with ignorance. Science isn't about eliminating all uncertainty, it's about quantifying and managing uncertainty, distinguishing between what we're confident about and what we're still figuring out. For 3I/ATLAS, scientists are confident that something unusual is happening. The observations are too consistent from too many independent sources to dismiss, but they're uncertain about the exact mechanism, the detailed explanation for why it's happening. That combination of confidence and uncertainty is perfectly normal and perfectly scientific. Uncertainty also plays a crucial role in driving research forward. If we were certain about everything, there would be no reason to keep observing, keep measuring, keep thinking. It's the uncertainties, the questions we can't yet answer, that make science exciting and necessary. Sometimes uncertainty is frustrating. We want answers, want to know definitely what's happening with 3I/ATLAS. But other times, uncertainty is liberating. It means the universe still has mysteries, still has phenomena we don't fully understand, still has the capacity to surprise us. Embracing uncertainty, living with it comfortably while working to reduce it, is a skill that scientists develop. It requires intellectual humility, the willingness to say, "I don't know," and mean it honestly. It requires distinguishing between degrees of certainty, recognizing that some things are well established while others are speculative. For those of us who aren't professional scientists but who follow science with interest, developing comfort with uncertainty is equally valuable. It allows us to appreciate the provisional nature of scientific knowledge while still trusting the overall reliability of the scientific method. It helps us distinguish between genuine scientific uncertainty and manufactured doubt designed to confuse or mislead. 3I/ATLAS, with its mysterious shape changes and competing explanations, is an excellent case study in scientific uncertainty. We can follow the story, watch as observations accumulate and models develop, and see how uncertainty gradually narrows even if it never entirely disappears. The story of 3I/ATLAS isn't the first time astronomers have observed something that challenged their understanding of how celestial objects should behave. Looking at historical parallels can provide perspective and maybe even hope that today's mysteries will eventually be understood. Consider comets themselves. For most of human history, comets were mysterious and frightening apparitions, appearing without warning in the night sky. They didn't follow the orderly motions of stars or planets. They seemed to violate the celestial harmony that philosophers and astronomers tried to understand. Aristotle, in the 4th century BCE, argued that comets weren't celestial objects at all, but atmospheric phenomena, like meteors or the aurora. This was partly because he believed the heavens were perfect and unchanging, and comets were clearly temporary and irregular. If comets existed in the celestial realm, they would violate that perfection. This view persisted for nearly 2,000 years. Not until 1577, when Danish astronomer Tycho Brahe made careful measurements of a bright comet, was it conclusively demonstrated that comets were indeed distant celestial objects, farther away than the moon. Tycho measured the comet's parallax, the apparent shift in position when viewed from different locations, and found it was too small for a nearby atmospheric phenomenon. Even then, the nature of comets remained mysterious. What were they made of? Why did they have tails? Where did they come from? Isaac Newton, in the 17th century, showed that comets followed elliptical orbits around the Sun, just like planets, which was a major step toward understanding. Edmund Halley used Newton's mathematics to predict that a particular comet would return in 1758, and when it did, it confirmed that comets were regular members of the solar system. But the composition and behaviour of comets weren't understood until the 20th century. The idea that comets were dirty snowballs, proposed by Fred Whipple in 1950, wasn't confirmed until spacecraft actually visited comets in the 1980s and 1990s, sending back images and data that validated the icy nucleus model. Each step in understanding comets took decades or centuries. Observations that seemed impossible or contradictory eventually made sense when viewed in the right framework with the right data. Another parallel comes from the study of asteroids. When the first asteroids were discovered in the early 19th century, they didn't fit expectations. They were too small to be planets, but too numerous to be occasional curiosities. Astronomers didn't initially have a framework for understanding them. Over time, as more asteroids were discovered and studied, patterns emerged. They occupied a region between Mars and Jupiter. They had irregular shapes. They came in different types with different compositions. Eventually, asteroids were understood as remnants of planet formation, leftover material that never coalesced into a planet, probably because Jupiter's gravity prevented it. But even within that understanding, individual asteroids could surprise. Some asteroids turned out to be binary systems, two objects orbiting each other. Some showed signs of past activity, outgassing like comets despite being classified as asteroids. Some had moons of their own. Each discovery expanded the category of asteroid to include more diversity than were initially imagined. 3I/ATLAS fits into this pattern. It's showing us behaviour we didn't expect, behaviour that doesn't fit neatly into our current models of cometary activity. But historically, such surprises are the rule rather than the exception. The universe is more diverse, more complex, more subtle than our models initially capture. The lesson from history is patience. Mysteries don't always resolve quickly. Sometimes a single observation or mission provides the crucial data that makes everything clear. Other times, understanding emerges gradually as many observations from many sources accumulate. For 3I/ATLAS, we're probably in the gradual accumulation phase. Each observation adds a small piece to the puzzle. Each model tested adds to our understanding even when it doesn't fully succeed. Eventually, perhaps years or decades from now, someone will look back at all the data and all the theoretical work and see the pattern that wasn't obvious to those of us watching it unfold in real time. That's how science works. It's messy, uncertain, full of false starts and abandoned hypotheses. But it's also self-correcting, progressive, building toward understanding even when individual steps seem confused. Behind every observation of 3I/ATLAS, every measurement and every model, there are people, astronomers, students, technicians, often working long hours in the cold darkness at telescopes, or hunched over computers analysing data, driven by curiosity and the desire to understand. It's worth pausing to appreciate the human dimension of this story because science isn't an impersonal process. It's done by people with motivations, frustrations, biases and hopes. The graduate student who noticed the first hints of unusual elongation in their data probably felt a mixture of excitement and doubt. Excitement because they might be seeing something genuinely new, something that could make their thesis or their career. Doubt because unusual observations are often errors. And claiming a discovery only to have it disproven is embarrassing. So they checked and rechecked their analysis. They showed their results to their advisor, who probably raised skeptical questions and suggested alternative explanations to consider. They might have spent weeks convincing themselves the effect was real before feeling confident enough to tell other astronomers. When other teams began reporting similar observations, there was probably relief. Independent confirmation is gold in science. It transforms quote 21 quote into quote 22 quote, but with confirmation comes pressure. Now there are expectations, other astronomers are paying attention, asking questions, proposing theories. Papers need to be written, data needs to be made available to the community, claims need to be backed up with rigorous analysis. Different research teams probably have different opinions about what's happening with 3I/ATLAS. Some favour the outgassing hypothesis, others prefer fragmentation, still others think it's something we haven't thought of yet. These disagreements aren't failures, they're how science works. Different perspectives, different interpretations, tested against each other and against new data. There might be friendly rivalries between teams racing to publish the definitive analysis. There might be collaborations forming, pooling data and expertise to tackle the problem from multiple angles. There are probably email threads full of debate, conference presentations where theories are presented and critiqued, and informal conversations over coffee where the real thinking often happens. The astronomers working on 3I/ATLAS are also juggling other responsibilities. They're teaching classes, serving on committees, writing grant proposals to fund their research, mentoring students, and trying to maintain some semblance of work-life balance. The study of one unusual comet, however fascinating, is just part of their professional lives. And they're working within a system that has its own pressures and incentives. Publications matter for careers. Novel results are more publishable than confirmations of existing knowledge. There's a subtle pressure to find something exciting, something newsworthy, even while maintaining scientific rigour. Most scientists navigate these pressures well, maintaining their integrity and letting the data guide their conclusions. But the pressures exist and they shape how research unfolds. There's also the challenge of communication. How do you explain 3i/ATLAS to the public in a way that's accurate but also engaging? How do you convey uncertainty without seeming wishy-washy? How do you push back on sensationalized interpretations without seeming defensive? Some astronomers are skilled communicators who enjoy engaging with the public. They write blog posts, give talks, appear on podcasts or documentaries, sharing their excitement and knowledge. Others are more comfortable with the technical work and prefer to let their papers speak for themselves. All of this human dimension is invisible in the published papers, which present a clean, logical progression of observation, analysis, and conclusion. But behind that clean presentation is a messy human process of discovery, and that's beautiful. Science isn't done by machines or AI, at least not yet. It's done by curious humans using their intelligence and creativity and stubbornness to understand the universe. They make mistakes, argue with each other, sometimes go down dead ends, but collectively they move toward understanding. The story of 3i/ATLAS is their story as much as it is the story of a distant comet. And that makes it, in its way, a human story, a story of our species trying to comprehend the cosmos we find ourselves in. As 3i/ATLAS recedes from our solar system, heading back into the dark vastness it came from, it's worth contemplating the nature of the space between stars, because that's where this comet has spent most of its existence and where it will spend its future. Interstellar space is almost incomprehensibly empty. In our everyday experience, even the best vacuum we can create on Earth contains millions of atoms per cubic centimetre. The air you're breathing right now contains about 10 to the power of 19 molecules per cubic centimetre, a number so large it's hard to grasp. In interstellar space, the density drops to perhaps 1 atom per cubic centimetre in the regions between star systems. In some regions, it's even lower, 1 atom per several cubic centimetres. This is emptiness beyond our intuition's ability to comprehend. If you could somehow exist in interstellar space, floating between stars, what would you see? The stars themselves would be brilliant points of light, thousands or millions of them visible in every direction, unblinking because there's no atmosphere to make them twinkle. But they'd all be distant, the nearest perhaps light years away. There would be no sun dominating the sky, no source of warmth or illumination. The temperature would be about 2.7 Kelvin, nearly absolute zero, maintained only by the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang itself. The cold would be profound and absolute. Nothing would protect you from it except whatever insulation you brought with you, and the silence would be perfect, total, because sound requires a medium to propagate through, and the interstellar medium is far too tenuous to carry sound waves. This is the environment that 3i/ATLAS knows best. For the vast majority of its billions of years' existence, this is where it has been. In the cold, empty dark between stars, travelling at several dozen kilometres per second, which sounds fast but is achingly slow compared to the distances involved. At 30 kilometres per second, a typical speed for interstellar objects crossing a single light year takes about 10,000 years. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. If 3i/ATLAS were heading directly there, which it's not, the journey would take over 40,000 years. But 3i/ATLAS isn't heading toward any particular star. Its trajectory is essentially random, determined by the gravitational kick it received when it was ejected from its home system and modified slightly by its passage through our solar system. It will wander through the galaxy, occasionally passing near a star, much more often travelling through the empty spaces between them. The galaxy is vast. It contains several 100 billion stars spread across a disk about 100,000 light-years in diameter. Stars are separated by average distances of a few light-years. This means that even travelling for billions of years, 3i/ATLAS will probably encounter only a handful of stellar systems. most of its existence will be spent in transit, in the cold and dark, unchanging and unobserved, a tiny frozen rock carrying the chemical signature of a star system it left eons ago. This is the fate of countless objects in our galaxy. Every star system produces them, ejecting comets and asteroids through planetary interactions. They accumulate in the interstellar medium like messages in bottles, drifting through the cosmic ocean, most never to be read. We've now read 3 of these messages: Oumuamua, 2 I/Borisov, and 3 I/Atlas. Each tells a story, fragmentary and puzzling, but genuine. They carry information about conditions and processes in stellar systems we'll probably never visit, chemical compositions we can barely measure, histories we can only guess at. And they remind us of the scale of the universe. Our solar system, as vast as it seems when you contemplate the distances from Earth to the outer planets, is a tiny island in an ocean of space. The distances between stars are so much larger than the distances within a star system that they require a different scale of thinking entirely. Yet somehow, across these vast distances, these tiny objects travel, and occasionally, very occasionally, one passes close enough to our small corner of the galaxy that we notice it, observe it, wonder about it. One of the most profound aspects of studying interstellar objects like 3I/ATLAS is what they can tell us about the chemistry of other star systems, about the elements and compounds that exist elsewhere in the galaxy. The universe, at its beginning, consisted almost entirely of hydrogen and helium, the simplest elements. Every other element, everything heavier than helium, has been created inside stars through nuclear fusion, or in the explosive deaths of stars as supernovae. Stars are element factories. In their cores, under immense temperature and pressure, hydrogen fuses into helium, helium fuses into carbon and oxygen, and in the most massive stars the fusion chain continues, creating neon, magnesium, silicon, and eventually iron. Elements heavier than iron are created in supernova explosions, when a massive star's core collapses and then rebounds, generating energies and densities that drive exotic nuclear reactions. When stars die, whether gradually as planetary nebulae or explosively as supernovae, they release these newly created elements into the interstellar medium. The next generation of stars forms from gas clouds enriched with these elements. Planets, asteroids, and comets forming around those stars incorporate these elements into their structure. This means that the composition of objects in a star system depends on the system's chemical history. A star system that formed early in the galaxy's history, from gas that had been processed by only a few previous generations of stars, will be depleted in heavy elements. A system that formed more recently, from gas enriched by many stellar generations, will be richer in elements like carbon, nitrogen, oxygen, and metals. The Sun and our solar system have an intermediate composition, reflecting about 4.6 billion years of galactic chemical evolution. We know this composition well because we can study it directly in solar system objects. But 3I/ATLAS comes from somewhere else, a system with potentially different chemical history. By analysing its spectrum, measuring which elements and compounds are present and in what abundances, we can glimpse the chemistry of its home system. The preliminary spectroscopic data from 3I/ATLAS shows a composition broadly similar to solar system comets, but with subtle differences. The ratio of carbon monoxide to water appears higher than typical for our comets. Certain spectral features suggest the possible presence of organic compounds, complex carbon-based molecules, in proportions that might differ from what we see locally. These differences are tantalizing because they suggest variation in planetary chemistry across the galaxy. If comets in different star systems have detectably different compositions, that tells us something about the conditions under which they formed, about the temperature and pressure in their protoplanetary disks, about the abundances of elements available during planet formation. This matters for understanding not just comets, but planets, and potentially life. The chemistry of a star system determines what kinds of planets can form. A system rich in carbon might form more carbon planets with silicon carbide and graphite mantles. A system rich in water might form ocean worlds. A system with abundant organic compounds might have better prospects for developing life. Every interstellar visitor carries this information with it, coded in its composition. By studying enough of them, we can start to map the chemical diversity of the galaxy, understanding not just the average composition, but the range of variation. This is a form of exploration as profound as sending spacecraft to distant stars, though much less direct. We can't travel to these other systems, but they send us samples, carried by gravity and time across the light years. We catch these samples, analyse them, and piece together a picture of worlds we'll never see. There's something deeply poetic about this. The atoms in 3I/ATLAS, the water molecules, the carbon compounds, the dust grains, were created in the cores of ancient stars or in supernova explosions billions of years ago. They condensed in a protoplanetary disk around a star we can't identify, were assembled into a comet through countless gentle collisions, were ejected into interstellar space through gravitational interactions, and travelled for who knows how long through the dark before arriving here. Now they're receding again, carrying their story back into the void. But for a brief moment their light touched our telescopes, and we could read, however imperfectly, the chemical tale they have to tell. When we observe something like 3I/ATLAS, with its puzzling behaviour and mysterious origin, a very human question arises. Why? Not why in the mechanistic sense of quote 23, but why in the deeper sense of quote 24, this question might seem unscientific. Science deals with how things work, not why they exist in some teleological sense. The universe doesn't owe us meaning or purpose. Phenomena occur because physical laws operate, not because of any grand design or intention. And yet the question persists, perhaps because we're meaning-seeking creatures who can't help but look for purpose and significance in the things we observe. One perspective is that 3I/ATLAS exists and behaves as it does simply because of natural processes operating over vast timescales. It formed because gravity caused material in a protoplanetary disk to coalesce. It was ejected because gravitational interactions with planets are common and inevitable. It changes shape, if that's indeed what's happening, because of some combination of composition, structure, and forces acting on it. There's no purpose beyond the mechanical operation of physical law. This perspective is scientifically sound and philosophically defensible. It doesn't require anything beyond what we can measure and test. It acknowledges that the universe operates according to rules we can discover but didn't design. But there's another perspective that doesn't contradict the first but adds a layer of meaning. From this view, the purpose of 3I/ATLAS is what we make of it. Its purpose is to teach us, to expand our understanding, to remind us of the vastness and diversity of the cosmos. Every phenomenon in nature can be both a mechanical occurrence and an opportunity for learning. 3I/ATLAS operates according to physical law, but for us, observing it, it becomes a teacher. It shows us the limits of our knowledge. It challenges our assumptions. It invites us to think more deeply about comets, about interstellar objects, about the processes that shape the universe. In this sense, the quote 25 of 3I/ATLAS is whatever purpose we find in studying it. For astronomers, it's an opportunity to advance science, to solve puzzles, to contribute to human knowledge. For students, it might be an inspiring example of the unknown, a mystery that draws them into careers in science. For the rest of us, it might be a reminder to look up, to wonder, to appreciate that we live in a universe far stranger and more magnificent than everyday life suggests. There's also a cosmic perspective worth considering. 3I/ATLAS is one of countless objects wandering through the galaxy. Most will never be observed by anyone. They'll drift through the darkness for billions of years, experiencing nothing, affecting nothing, existing without purpose or meaning in any conventional sense. But a tiny fraction of these objects by chance pass through stellar systems. An even tinier fraction pass close enough to planets with intelligent life capable of observing them. 3I/ATLAS won the cosmic lottery in that sense. Of all the interstellar objects in the galaxy, it happened to pass through a system where beings existed who could notice it, measure it, wonder about it. Is there purpose in that? Perhaps only the purpose of bearing witness. 3I/ATLAS was always going to pass through our solar system, whether we observed it or not. The fact that we did observe it doesn't change its trajectory or its fate, but it changes us. It adds to our knowledge, our experience, our sense of connection to the larger universe. Maybe that's enough. Maybe the purpose of remarkable phenomena isn't something inherent in the phenomena themselves, but something that emerges in the interaction between the phenomena and conscious minds capable of appreciating them. A sunset is just photons scattering through an atmosphere, but it becomes beautiful when someone is there to see it. A piece of music is just pressure waves in air, but it becomes meaningful when someone is there to hear it and feel it. And 3I/ATLAS is just a comet. Ice and rock obeying physical laws, but it becomes significant because we're here to observe it and wonder about it. This isn't to say that human observation is necessary for things to matter. The universe existed for billions of years before conscious beings evolved, and it mattered then too, in whatever way things matter without anyone to care about them. But for us, as conscious beings, the meaning and purpose of things is inevitably tied to our awareness of them. So perhaps the purpose of 3I/ATLAS is simply to be observed, to be wondered about, to be a small part of the larger tapestry of cosmic exploration that our species has undertaken. That might seem like a small purpose, but in the vastness of the universe, where most things go unobserved and unconsidered, being noticed might be purpose enough. Astronomy teaches patience in a way few other endeavours can match. And 3I/ATLAS is an excellent example of why that patience is necessary and valuable. The comet was probably ejected from its home system millions or billions of years ago. It travelled through interstellar space for an unimaginable length of time. It passed through our solar system over a period of several months in 2024, and now it's leaving, receding back into the darkness, and we'll never see it again. Our window of observation was brief. Cosmically speaking, a few months to gather all the data we could, a few years to analyse that data thoroughly, perhaps a few more years to publish papers, propose theories, debate interpretations, and then the active study of 3I/ATLAS will wind down, preserved in the scientific literature as a case study, a mystery partially understood, a puzzle for future researchers to contemplate. This is typical of astronomy. We don't get to control our subjects or determine the timeline. We observe what the universe presents to us, when it presents it, and work with whatever data we can gather in the time available. Sometimes patience is rewarded dramatically. Halley's Comet returns every 76 years, and each apparition provides new opportunities for observation with better instruments. Over centuries, our understanding of Halley's Comet has deepened with each return. But 3I/ATLAS won't return. Its orbit is hyperbolic. It came from interstellar space, and to interstellar space it returns, never to come back. We had one chance to study it, and now that chance is past. This creates a particular kind of poignancy in astronomy. The objects we study are often unique, unrepeatable. We can't go back and get more data if we realise later that we missed something important. We can't run the experiment again with better controls. We can only work with what we have, acknowledge what we don't know, and hope that someday another similar object will appear and provide the additional information we need. This requires a long view, a patience that extends across generations. The The astronomers studying 3I/ATLAS today won't be the ones who finally solve all its mysteries. Perhaps their students will make progress. Perhaps someone decades from now, studying the next strange interstellar comet, will have that, quote, 26 moment when everything clicks into place. Scientific progress often works this way. Individual scientists make small contributions, add tiny pieces to the puzzle, and the full picture emerges only gradually as many contributions accumulate. There's something humbling about this. It means that no individual's work is likely to be definitive. We're all just adding stones to a cairn being built across centuries. The satisfaction comes not from solving everything, but from contributing meaningfully to the collective endeavour. Patience is also required in dealing with uncertainty. When the first observations of 3I/ATLAS's shape changes were reported, there was probably an impulse to jump to conclusions to explain it immediately. But science requires resisting that impulse, sitting with uncertainty, gathering more data, thinking carefully. Years may pass between initial observations and published papers. More years may pass before consensus emerges. Some questions may never be fully answered. This glacial pace can be frustrating for researchers and for those of us following their work. But it's also necessary. Rushing to conclusions leads to errors. Taking time to think deeply, to consider alternatives, to test theories thoroughly, leads to more reliable understanding. There's a kind of meditation in this patience. Astronomy encourages contemplation, the slow consideration of phenomena across vast scales of time and space. You can't rush the movement of celestial objects. You can't speed up the travel time of light from distant sources. You simply have to wait, watch, and think. In our fast-paced modern world, this patience can feel countercultural. We're used to instant answers, immediate gratification, rapid resolution of questions. But the universe operates on its own timescale, indifferent to our impatience. Learning to match our pace to the universe's pace, to find satisfaction in gradual progress rather than immediate resolution, is a valuable skill. It applies beyond astronomy, to any long-term project or deep question. Some things simply can't be rushed. 3I/ATLAS, in its slow journey through our solar system and its slow revelation of its properties through careful observation, teaches this patience. It reminds us that some questions take time to answer, and that's okay. The universe isn't going anywhere, at least not on timescales that matter to human endeavours. We have time, we just need to use it wisely. As we near the end of our exploration of 3I/ATLAS, it's important to recognise that this isn't really an ending at all, but rather a pause in an ongoing story that will continue long after this conversation ends. Right now, as you listen to these words, 3I/ATLAS is still out there, moving through space. It's fainter now, harder to observe, receding beyond the reach of most telescopes, but it still exists, still follows its trajectory, still carries whatever secrets its composition and structure hold. Astronomers might still be gathering data, squeezing out a few more observations before the comet becomes too faint to see. Papers are probably being written, data analysed, theories refined. Conferences will feature presentations about 3I/ATLAS. Debates will continue in professional journals and informal conversations. And then, gradually, the active study will wind down. 3I/ATLAS will fade from the forefront of astronomical attention, becoming a historical case rather than a current mystery. New objects will be discovered, new puzzles will emerge, and the community's focus will shift. But the story won't end. The data will remain archived, available to future researchers. Someone decades from now, working on a different problem, might pull up the 3I/ATLAS observations and see a pattern no one noticed before. A new theory might emerge that finally explains the shape changes. Or perhaps 4I or 5I or 12I, some future interstellar visitor, will behave similarly. Providing comparative data that clarifies what happened with 3I/ATLAS Science is continuous. Individual projects have beginnings and ends, but the larger endeavour of understanding the universe continues across generations. Each generation builds on what came before, reinterprets old data with new insights, and adds its own contributions to the growing body of knowledge. The story of 3I/ATLAS is also part of the larger story of humanity's engagement with the cosmos. We're a species that looks up, that wonders, that seeks to understand. For most of our history, the stars were unreachable mysteries, objects of myth and speculation. Only in the past few centuries have we developed the tools to study them scientifically, and only in the past few decades have we reached the point where we can detect and study objects from other star systems passing through our cosmic neighbourhood. Oumuamua was the first, but it won't be the last. Improved surveys will find more, better instruments will study them in more detail, perhaps someday missions will visit them directly. Each discovery, each observation, each insight adds to our understanding not just of specific objects but of the universe as a whole. We're mapping the diversity of cosmic phenomena, learning what's possible, what's common, what's rare. 3I/ATLAS, strange as it is, becomes part of that map. It shows us that interstellar comets can behave in unexpected ways, that our models might need refinement, that the universe has more variety than we initially thought. This is valuable even if we never fully explain 3I/ATLAS. Knowing that something unexpected exists, that there are phenomena we don't yet understand, is itself a form of knowledge. It tells us where to look, what questions to ask, what theories need development. And beyond the scientific value, there's something deeply meaningful about the simple fact of engagement. We could ignore the sky, go about our daily lives without wondering about distant comets. But we don't. We choose to look, to wonder, to invest resources in understanding. This says something profound about human nature. We're curious beings. We want to know even when the knowledge has no obvious practical application. We're willing to spend time and effort studying objects that will never affect our daily lives, simply because they exist and we can learn about them. 3I/ATLAS will never change your life directly. It won't cure diseases, won't solve economic problems, won't make your day easier, but it might change how you think about the universe, might spark a sense of wonder, might remind you that there's more to existence than the immediate concerns of everyday life. And that has value too, not practical value perhaps, but the value of enrichment, of perspective, of connection to something larger than ourselves. The story of 3I/ATLAS continues, then, not just in scientific papers and future observations, but in the minds of everyone who learns about it and is moved to wonder. It continues in the students who might be inspired to study astronomy, in the conversations about cosmic mysteries, in the quiet contemplation of a strange visitor from the stars. That's a story worth being part of, even if we'll never see its conclusion. Thank you for staying with me through this entire journey. We've travelled together for over 2 hours now, exploring the mystery of 3I/ATLAS, thinking about comets and interstellar space, contemplating the nature of scientific discovery and the vastness of the cosmos. I'm grateful for your time and your attention. We started with a simple question. Why is this interstellar comet changing shape? We explored the observations that puzzled astronomers, the measurements that seemed impossible, the various theories proposed to explain what we're seeing. We thought about the physics of comets, the nature of interstellar space, the history of astronomical discovery. And we arrive at the end of our exploration without a definitive answer, which is honest and appropriate. The truth is that we don't yet know for certain why 3I/ATLAS appears to be changing shape. We have theories, models, educated guesses. Some seem more plausible than others, but certainty eludes us, at least for now. The answer, as honestly as I can give it, is probably some combination of the comet's unusual composition, its structure, the forces acting on it as it warmed near the sun, and possibly processes we haven't fully considered. It might be fragmenting slowly, or deforming through outgassing forces, or experiencing complex rotation-driven redistribution of material. It's likely natural, likely explicable through physics we understand, but the specific mechanism remains uncertain, and that's okay. Not every mystery gets solved immediately. Some take time, patience, more data. Some might never be fully resolved. What matters is that we observed carefully, thought deeply, and expanded our understanding even if we didn't solve everything. If you enjoyed this slow drift through cosmic mysteries, I hope you'll consider liking and subscribing. And I'd love to hear your thoughts in the comments. What about 3I/ATLAS fascinates you most? What other cosmic mysteries would you like to explore together? Wherever you are in the world right now, I hope you're comfortable. I hope your breathing has slowed to a peaceful rhythm. I hope your thoughts have quieted, or at least settled into a gentle contemplation. I hope the day's worries have faded into the background, giving you space to simply be, here and now. Look up at the stars if you can see them from where you are, or if you can't, imagine them. All those points of light, each one a sun like ours, potentially surrounded by planets, moons, asteroids and comets. And between those stars, countless objects like 3I/ATLAS, wandering in the darkness, carrying stories of worlds we'll never visit. Somewhere out there, right now, 3I/ATLAS is moving through space, getting colder as it recedes from the sun, slowly returning to its dormant state. Its brief awakening in our solar system is ending. Soon it will be frozen again, unchanged, travelling through the void for who knows how long before it encounters another star. But for a few months, it was alive in a sense, active, changing, visible to us. We were here to witness it, to measure it, to wonder about it. And in that witnessing, in that wondering, we participated in something ancient and profound. The human desire to understand the universe we find ourselves in. There's beauty in that. Beauty in the mystery itself, in the questioning, in the slow process of discovery. The universe doesn't owe us answers, but it gives them anyway, gradually, to those patient enough to watch and wonder. Sleep well, wherever you are. Dream of wandering comets if you dream at all. Dream of long journeys through the darkness, of brief moments of warmth and light, of the vast patient turning of the cosmos. Dream of mysteries that invite contemplation, questions that have no easy answers, and the quiet satisfaction of simply looking up and wondering. Good night. May your rest be peaceful, your dreams cosmic, and your tomorrow filled with curiosity about this strange and beautiful universe we share. Good night.